तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In our last discussion, we saw, or we tried to see whether you can make MOS field effect transistors with gallium arsenide and indium phosphide, and it so turned out that it is a tough task because you do not have very good native oxide for gallium arsenide and indium phosphide. This problem becomes compounded because of the different vapor pressures of the oxides of the element. For example, oxide gallium trioxide and arsenic trioxide, those have different vapor pressures. All these put together, it is difficult, and also if you try to extend the technology further by annealing, etc., you find that there are elemental arsenic at the interface in the case of gallium arsenide, which actually leads to very high interface density, and it gives improper CV characteristics, which would imply FET is not giving proper performance in terms of good transconductance. What we are looking for finally is a good GM. At the very beginning we said GM by C is the figure of merit. GM must be large, and for GM must be large, the drain current change must be large for a given change in gate voltage. That will not happen, because for all the gate voltage changes, what response will not be the channel charge, it will be the interface charge, which does not give rise to drain current. So, with that we said it is not possible to make those devices with MOS. So, the solution is do not worry about the native oxide, make a JFET or metal semiconductor field effect transistor, that is the MESFET, metal semiconductor field effect transistor. Now, this has, we also just flashed this slide in our last presentation, this has ohmic contact to the n plus region source, ohmic contact, metal semiconductor contact, both of them, to the drain region, because after all you must take external connection to reach electrically to those regions, and then you have this metal semiconductor contact, which is rectifying contact. Now, we will see what are the requirements to make these devices, these contacts. So, we will get into, before going to that, few things I want to clarify. So, you have ohmic contacts and rectifying contacts. These are encountered everywhere, not merely for gallium arsenide or high speed, you encounter that in the case of silicon devices also. So, a bit of understanding of these devices, how to make them, etc., we will just open up. This is just an illustration of the ohmic contact. After all, ohmic contact should allow the current to flow through that, and you will have a linear characteristics in the forward and both directions. Okay. So, delta I by delta V is the slope of this line. Ideally, that slope must be infinite, vertically going up, but you can never have a current for nothing. You should have some voltage drop across the device, that should be minimum. When you say ohmic contact is good, you see that it is more and more vertical, this characteristic. Now, other one is rectifying contact, which all of us talk about it and worry about it throughout our discussions on devices and circuits. So, that actually will block current flow in one direction. Ideally a rectifying contact, an ideal contact should be like this. The ideal contact, rectifying contact should be it would conduct with 0 voltage. this is block with 0 current. We never get that. So, what you get in practice, this is ideal. What you get in practice is, all of us know, that is the forward, and in the reverse close to this, but on a different scale it will show like that. So, this is the practical. Rectifier. Okay, now we will get around and see how to realize this in practice. So, after all, you need at the source and drain that type of contact, at the gate you need this type of contact. It can be junction, diode, but now what we are talking of is a metal semiconductor contact which will behave like a p-n junction. So, now you are on to the energy band diagram of the metal semiconductor contact. Okay. We talk of, this diagram shows you the two materials, that is the metal and the semiconductor, which are not in contact, okay, and they are separated in space, no electrical connection. Now, on the left hand side here, right below this point, I have shown the Fermi level of the metal, EFM, Fermi level of the metal, and I have shown the vacuum level. So, this phi m, what you have put there with an arrow, is actually the work function of the metal. To talk in terms of energy, it is the energy difference between the vacuum level and the Fermi level. In terms of physical phenomena, it is the energy required to remove the electron from the Fermi level to the vacuum level outside the metal. That is an indication of that. So, that is the energy band diagram or the energy level diagram. This is for the case of the metal. Now, if you take semiconductor, I have put entire energy band diagram. Conduction band is EC, Fermi level EF, and valence band is GV. The very fact that I have drawn the Fermi level closer to conduction band tells you it is N type material. So, we are talking of a metal and a semiconductor and a N type semiconductor in general. Whatever we are talking of is true for silicon, gallium arsenide, indium phosphide, gallium nitride. Okay. So, now here a few things are there. Phi s is the work function of the semiconductor. Again you talk of the electron, the energy required to remove the electron from the Fermi level to the vacuum level. There are no electrons in the Fermi level, but conceptually you have to have a landmark to see from where you measure. So, that is the work function of the semiconductor. And here you have one more term, chi. The usual symbol that you use, chi, is the electron affinity of the electrons in the semiconductor. That is energy difference between the vacuum level and the conduction band edge. With those definitions, we can proceed further. So, you can see these are, there is a gap, this dotted line that I put there here, it shows the vacuum level. Now, next what we will see is bring them into contact. I will not move them closer, they are just close by enough, but I will connect them through external wire. This is all the definition that we have said just now. So, we do not have to go through that. That is, work function is energy difference between the vacuum level and the Fermi level. Phi m is the work function of the metal. Phi s is work function of the semiconductor. Energy difference between the vacuum level and the Fermi level in the semiconductor. Chi is the electron affinity of electrons in the conduction band of semiconductor between EC and vacuum level. So, when you bring them contact, all that I have done is I have not moved anything, I just connected them together. Okay. Now, let us go back to this diagram and see, original diagram, and see what is the situation. If you connect them together externally, what would happen we will see. The actual diagram we will see afterwards. See here, the Fermi level here is above the Fermi level here. The moment you connect them together, need not join them, bring them close enough, connect a wire between them. Now, just like in the case of p-n junction, there will be transfer of electrons from the semiconductor to the metal, because Fermi level is higher, above the Fermi level in the metal. EF is above EFM. So, result is the probability of occupation when the system must be the same thing with reference to the Fermi level. So, the Fermi level will immediately equalize, and to equalize the Fermi level, the electrons will move from here to here. In fact, what is happening is you find that there are a lot of electrons here much higher than this level where there are energies available. So, if there are energies available, the electrons will go and occupy that level. That is what happens. Electrons from this level get transferred onto these levels which are available in the metal. So, once the electrons are transferred, what happens? That is what we are seeing here. The electrons from this region are transferred through the metal here onto the other side. That means the metal is negatively charged and the semiconductor is positively charged. And from the Coulomb's law of force, you can see that whatever happens to the closest points. Minus charges will be present on this side, and the plus charges will be present on this side. So, if you just see the diagram there, what happens is I have the metal, that is the metal. I have the semiconductor. I am just drawing that because some of things are not clear there. This is N type semiconductor, S. This is metal. I have connected them together. So, what has happened is this has acquired negative charge because of transfer of electrons from there to here to equalize the Fermi level. Now, this has plus charge. The number of electrons or the doping concentration in the N region 10 to the power of 15, 16. Here electron concentration is metal 10 to the power of 22 and above. So, if you put in few electrons here, it is not going to occupy space, it will be just a mono layer of that will give that negative charge. So, you have negative charge here. The net positive charge will come from a finite width. So, there will be depletion layer. So, the moment you connect, because of transfer of electrons from the semiconductor to the metal, because Fermi level is above, so electrons will get transferred till the Fermi levels are equalized. I have drawn the diagram which is finally equalized, and the equilibrium condition we have drawn that. So, when you do that, there is a depletion layer. In fact, this diagram I have not shown there, but if you look at the energy band diagram, the Fermi levels have got equalized because of transfer. The whole thing is because now the energy band diagram has tilted with this side positive and that side negative. Wherever the band bending is there is potential change. So, there is potential change from this end to that end. This is plus and this is minus. So, the charges which originate over this region, they terminate here. You can just see this here. If you see this gap which I have marked there, there are electric fields like this, there is electric field like this, electric field going into that. So, let me draw it a bit better. I draw 3 here, 1, 2, 3, the foot here, they will come down like this. That is the electric field. Number of electric field which cross will be equal to how many electrons have moved from here to here. For one electron which has moved from here to here through the outside wire, you have got one positive charge and one negative charge. So, that one field line is there. So, once you have connected them together, the charge here and charge here is fixed. That means the electric field here is fixed. How much is the potential drop here depends upon how much is the gap. Electric field into the distance here is the potential drop, linear. That is what is put here. That is the vacuum level. The vacuum level itself tilts now. So, this slope here indicates that there is a constant electric field, therefore, linear voltage drop across that point. So, the conduction band or the vacuum level here is going linearly like that. And you can see this particular portion here, that is not linear, because you know that whenever there is a abrupt junction, wherever there is a depletion layer, the voltage is square law. So, that is what is shown by this portion. So, you got the voltage change here, that is shown by the change in the conduction band variation, and beyond a certain point it is flat, and it is flat beyond this portion, because this is neutral region, there is no voltage drop. When there is no voltage drop, band diagrams are flat, that is shown in that portion. Here there is a variation in the band diagram, because there is a potential change from here to here. This is positive, this is minus, this is positive, this is minus. So, there is a drop V I in the intermediate level, and there is a drop in the semiconductor corresponding to this position and this position. Whatever is the slope like this, if I have a slope like that, there is a drop in the semiconductor. Okay? So, what I want you to note here is that the voltage drop V I for these two semiconductors depends upon how much is the gap. This band bending is fixed, because number of electrons which have moved are decided by how much is the difference between the phi m and phi s. Go back to that. This phi m and phi s, this difference between this level and that level, that is the total potential change that you get from one end to the other end. So, now let us go back to this. So, when you move into this particular thing, this, if I reduce the delta, that drop will be reduced. That drop will be reduced, but the charge within the particular region is the same thing. The number of electrons which have moved is the same thing. Okay. Otherwise, the energy band diagram has remained the same practically. All that has happened is this drop has changed, reduced. Okay. I am keeping on reducing it, because we are talking of not MOS or MIS, we are talking of MS, further reduced. Okay. Now, you can see the entire drop is in the semiconductor, and the drop here is very, very small. Okay. So, if I have electrons here up to this point here, there is a possibility that they can cross this when it is thin, because when the oxide becomes very thin, okay, and if there are states available on the other side, which actually is present here, this is the conduction band of the semiconductor, electrons can cross if they have enough energy. Okay. So, there is a chance for that to flow. Now, what we are talking of is not even that layer present. Okay. Electrons with energy, greater than this phi Bn can cross this way or that way. Thermal equilibrium, of course there will not be any net current flow, because what crosses from this side to that side will balance each other. Now, look at what we have done. We have removed even that layer. So far, we are doing the whole thing with a contact. Removed that, I removed that contact now. That is, I have removed that external connection. Just put that. Now, it is in intimate contact. The metal M is in intimate contact with that. There can be exchange of electrons directly through that. Don't have to go through external path. So, all that has happened is we have shown finally with this. With the metal contact itself, you have brought it together like that. That is the diagram. Now, if you remove the metal contact, also there is no problem. So, now you can see the vacuum level phi m. This is the conduction band is there, chi up to the vacuum level, and what else? Phi s is from here to that point, okay, from here to that point. But just one thing I want to point out here, I have not drawn the vacuum level on this side. How will the vacuum level be on that side? See, we have not shown, even here I have not shown the vacuum level at that point. So, the vacuum level will show wherever the potential change is there, it will follow the same path. So, I just draw that for completeness sake. So, what we are trying to see is, you have the contact like this. I am redrawing the diagram, okay? The conduction band, valence band, etc. This is where up to where the depletion layer is present. Then I am putting this Fermi level here in contact, aligned with the respect to each other, just like in the case of p-n junction, EC, EV. Now, what we are showing there is the vacuum level, that is the vacuum level, and this is phi m. I am redrawing it here for clarity, and this is actually equal to chi. Wherever potential changes take place except Fermi level, all other energy levels follow the same path. So, this level also will go from here, it will go like that. We have taken a situation where phi m is greater than phi s. Okay, you go back to this diagram and see, starting diagram, if you go back, just notice here, right at the beginning I have put it there, phi m is greater than phi s. That means actually this Fermi level is, the difference between the vacuum level and Fermi level here is more than the difference between the vacuum level and Fermi level, which means the Fermi level is here is above the Fermi level there. Now, finally, what happened is this Fermi level has come down because of transfer of electrons and the potential has appeared. So, that is what we have shown there. Okay. So, phi m is greater than phi s. Okay. Now, this level, this quantity is phi b n. That is the quantity which we are looking for, because that is actually the barrier for electrons from this side. If there are electrons in the metal, to cross from there to here, it has to go up this barrier. Okay, because if there are electrons here, if there are levels on the right hand side, it can go cross. There are no levels. So, if at all it has to move to the metal, it should have sufficient energy so as to go into the region where energy levels are present, conduction band. Now, look at the semiconductor portion. Between this neutral portion and the surface, there is a potential change. There is a potential change, and that potential change is VBI, which you can call it as built-in potential. Like in the case of p-n junction, it is exactly like in the case of p-n junction. You have the built-in potential VBI, and that VBI in terms of energy Q VBI is equal to, that is this VBI, that is the Q times VBI, because that is the energy band diagram that we are showing off, Q times VBI, that is equal to phi b n minus this. Phi b n is this quantity minus this E c minus E f, that is Q VBI. Okay. So, now what is phi b m? Phi b n? Phi b n is actually phi m minus chi. Okay. This quantity is this minus that, phi m minus chi. So, once you fixed a semiconductor and a metal, phi m is fixed. Okay. In a particular semiconductor, once you fix the metal, phi m is once you choose the metal, phi m is fixed, and once you choose metal and semiconductor, that is fixed, because phi b n is actually equal to there, phi m minus chi. Okay, I just redrawn the thing so that further clarity is there. That is, this phi m minus chi is phi b n, that is that. Okay, chi is fixed by semiconductor, it is independent of doping, you can see that, it is only dependent on the work function. Then this built-in potential depends upon, in addition to that phi b n, it depends upon E c minus E f, that is actually a doping level. If the doping is increased, Fermi level goes towards the conduction band. So, that is actually built-in potential. Okay. So, you will have slightly, if it moves up, you will have slight reduction in the VBI. That will be, we will come back to those discussions. Right now, what I am focusing is this quantity mainly, okay, and that decides what is the built-in potential is, guided by the doping of the material. Okay. Notice here, this is the barrier height for electrons to move from the metal to the semiconductor, and correspondingly you can mark a barrier height here for transfer of holes in this direction, that is phi b p, and phi b p is this quantity. Okay, that is phi b p, and that quantity is, what is this much? E g, band gap minus phi b n is phi b p. So, the moment you fix metal, phi m is fixed, moment you choose the semiconductor, chi is fixed, so phi b n is fixed, and once you fix phi b n, phi b p is given by that E g minus phi b n, because for a semiconductor E g is fixed. These are known fixed quantities, okay, independent of doping. So, it looks from here that the main player in the game is phi m, metal work function, because that is the one which decides barrier for electrons and barrier for holes. Why are we worried so much about barrier? The barrier is the one which allow or not allow the electrons to flow. Take a look at that. Now, this is the diagram which I have just redrawn, that removing all other unwanted things, just only the main particles which participate in the conduction mechanism. So, this is the phi b n, and we are still talking of n type material, because p type we can work out same way. So, this is the phi b n from there to here. Okay. So, this is the phi b n, whether it is not very clear. Phi b n refers to this point, not the whole thing. Okay. This phi b n should come, okay, just redraw that. So, it will become clearer then. So, what we have drawn there is like this simple diagram, like that, and the Fermi level here like this. This is of course parallel to that. That is what we have done. Again, okay. Now, what I have drawn is this distribution. This is phi b n. Okay, that somehow that point what I put there is referring to this barrier height. That you know by now. That is the barrier height. So, this phi b, this is the phi b n. Okay. What I put here is that line corresponding to the tip of that. What does this mean? This actually, if you closely observe, I have just drawn it like that. This is the electron distribution of electrons in the metal as energy goes up. After all, Fermi level is defined as the level up to which electrons are occupied at 0 temperature. When you raise the temperature at room temperature, many of the electrons find themselves energy above the Fermi level, and this is the distribution. The probability of occupation goes on decreasing as you go up. This is actually the probability of distribution. In a metal, there are a number of levels which are present there, but the whole thing is guided by the probability. This is virtually the probability distribution function that I have plotted. So, this does not go into that, does not become 0, it is there. So, what I am telling is, you will have electrons energy above this barrier, some of them. These electrons have energy over and above the barrier. Okay? Now, look at the semiconductor. There also I plotted that is the like that. What does it mean? That means the conduction band is here, valence band is here. This is product of density of states available in the conduction band multiplied by probability. Okay. And how does it come? This quantity is coming like this. Density of states actually is going like this, square root of E minus E c, and probability function goes like this. So, this is F e Fermi-Dirac distribution function, and this is what symbol do you use? G e, density of states. Product of those two, F e into G e gives you n as a function of energy. That is what you are plotting there. Product of these two will be this 0 multiplied by something 0. So, it goes up like that. That is how it is. That is what you have plotted there. So, this is actually the distribution of electrons. Now, that is what I put here. So, you have electrons like that. Now, you can see the Fermi level has adjusted itself ultimately by transferring electrons from the semiconductor to the metal in thermal equilibrium, such that the distribution tip here, distribution tip there almost match, which would mean under thermal equilibrium conditions the number of electrons above that if you integrate and number of electrons if you integrate above that, they should be same thing, because these electrons can cross this way like this, they can cross this way like this. Number crossing from metal to semiconductor will be equal to number crossing from semiconductor to metal. Thermal equilibrium situation. Thermal equilibrium means you do not apply any voltage, do not put light. It is energy exchange is between ambient temperature is the guiding line, nothing else is there. The semiconductor is in equilibrium, or the entire system is in equilibrium with the particular temperature. Okay. So, that is what I have put there. So, just note that this phi b n refers to this height. Okay. Now, what I have put here I naught. What is that I naught? If you understand this, we can quickly rush through go through the whole thing. This quantity gives rise to the current I naught here, and this quantity gives rise to current I naught here. That is what I have marked. All those electrons which have energy above this barrier, that is on left hand side, that portion what I have circled here, they will be crossing this barrier. There is no barrier, that will give rise to current I naught. These electrons which have energy above that, that should give the rise to current I naught to compensate. In other words, what you are telling is net flow of electrons is 0, I naught from there, I naught from here. If you disturb that, you will be disturbing that current injected from left hand side and right hand side. Okay? So, this is the situation in thermal equilibrium conditions. Now, if you apply bias to the semiconductor, okay, what will happen? Just notice that of thermal equilibrium, I just applied a reverse bias. I made this region positive. This is thermal equilibrium. If I make this region positive, what happens? Let us just remove these things now. I just put this diagram here. Okay. That is the junction, metal semiconductor junction, if you want to call metal, and this is the n type. So, originally you had this that is the depletion layer. When I apply reverse bias, what happens? Where does the potential go? It will appear only into the space charge region. It will appear only in the semiconductor, because the charges here will be right on the surface available, minus charges. So, it will actually widen, and if it widens, what happens to this height? Whatever was BBI will become more. So, that is what has happened now. So, that is what you have seen here. Okay. Here the Fermi levels are same. Now, this portion, as it is, the entire thing comes down. So, the Fermi level here in the neutral portion will come down, that is shown here. Okay.
What about the right hand side? Electrons will repel electrons through this.
We will come back to that. Okay. See, what is happening is the right hand side electrons here, they have been taken out in this direction. The moment to switch on, there is a transient which will pull from here to here. These electrons are there, they will open up, depletion layer will widen by removing the electrons from here to that side. When you apply a battery, what do you do? When the depletion layer is moved here, you have removed the negative charges from here more, and those negative charges have gone from this path like this to this side. So, your field has gone up there, the peak field has gone up here, the potential drop has increased. Okay. I hope I have answered your question. So, that is why you have got the potential change from here to here has increased. This what was originally that potential QVBI has now become equal to QVBI plus VR. VR is applied voltage. Okay. What is the consequence of this? That is the diagram which I do not have to draw, you can see here. What you have to see is the neutral portion, whole thing has come down, and this portion is slightly widened. So, when the neutral portion comes down, what happens? You don't, I have drawn it there already. So, originally it was here, now it has come up to this point. So, what was here originally has come down to some extent like this. I have drawn it magnified, that has come down like that. That is, the neutral point has come down like the conduction band, and valence band correspondingly has gone down. So, EC and EV in the neutral region remains the same thing, the gap, but only its energy has lowered down because of plus charge on the other side. Now, what about this portion now? What was originally here, which was going above that like that, which was, some of them were able to cross. Okay. This level, this is the kinetic energy of the electrons. The kinetic energy is 0, the entire energy is potential energy here. So, as you go up, that is thermal energy because of that kinetic energy. When you push the conduction band down, you are bringing the potential energy down. The kinetic energy remains the same thing, guided by temperature. So, this distribution in the neutral region remains the same thing. The whole level has come down, and from here it is coming down like that. And you can't draw the Fermi level now here. You can't draw the Fermi level here, you draw it only there and call it as quasi Fermi level. Means actually you can still compute the electron density using this Fermi level with respect to conduction band. That is the meaning of quasi. You do not talk about that here. And from here, the whole thing comes down. Okay. So, that is the new energy band diagram. What is the consequence of that? These are just basic concepts which once it is clear, we can move further. What happened to this barrier? That barrier has not changed, because there is no depletion layer there. There is no potential drop across that. So, that barrier remained the same. Phi Bn does not change. So, now let me just draw this here. Once again, whatever you have got there, this Phi Bn has remained the same thing. Okay. So, as far as the electrons are concerned, distribution is concerned, here what has happened? We have drawn it earlier like that, thermal equilibrium situation. Whatever electrons are there, they can cross the barrier still, okay, that barrier has not changed. Whatever was giving rise to current electron transfer from left hand side metal to the semiconductor remains the same thing, that we called it as I naught. If that is continuously transferred, you will get a current I naught, and the direction of the current is actually transfer from here to here. Actual direction of current flow is like that, semiconductor to the metal. Okay? That is what I marked there. This is actually due to the extra electrons which have energy above this barrier. They can cross from this side to that side because that is a conduction band, and that will give rise to current I naught, which we call it as IMS. IMS is actually due to the electron flow from metal to semiconductor. It will be continuously flowing. So, that is why you get a current in the external circuit. It has got to be from the positive terminal of the battery, because that is the one which is driving the current. So, it goes from here to there and from semiconductor to metal. I have marked it IMS because MS telling you direction of electron flow from metal to semiconductor. I is the current actually which is flowing there, that is the direction. Okay. What happens to the current which was flowing from the semiconductor to the metal? You have pulled the potential energy down here. Originally when it was here, they were having energy like this. Let me draw it by dotted line before that. You had this energy band diagram like this. You had it like this. Those were the ones which were compensating for that thermal equilibrium condition to make the current equal to 0. Okay. Now, this current has not changed, I naught. What about this transfer of electrons from the semiconductor to the metal? That has dipped down, because these electrons, the maximum energy that these electrons have in the semiconductor is up to that point. Beyond that point, they can't cross the barrier. They don't have the energy to climb up the barrier. So, they stay there. So, the entire electron flow is due to the transfer of electrons from the metal to the semiconductor, which is actually I naught. And there is no transfer of electrons due from the semiconductor. So, now how much is I naught decides how much is the current now flowing here. How much is I naught depends upon this barrier. If that barrier height is small, okay, let me just draw that. Suppose I have a barrier like this, a barrier, I think you can figure it out right here. These electrons have energy above that. Suppose this barrier were smaller, this point is shifted up, more number of electrons will be having higher energy. Okay? So, if you shift the whole thing up, more electrons have the higher energy. So, phi Bn, if it is smaller, I naught will be larger. The current when you reverse bias will be larger if the phi Bn is smaller, because if phi Bn is smaller, you are lifting the left hand side up all the way. So, you will have more electrons which can cross that. Okay? You can look into it either way. You can just hold this here, pull this fellow down, the entire thing down, all these electrons will have energy up. Okay? Supposing I have this barrier only this much, all these electrons have that energy. So, what I am trying to point out is, if you want to cut down I naught, you must have higher IBN, phi Bn. That is what you have to do. So, this is a key thing whether you want to decide a rectifier or a ohmic contact. Okay. Now, let us see what happens. So, and this barrier now you see how much is this barrier depends upon VBI plus VR. VBI was just enough to compensate for I naught. Once we have put VR sufficiently large, I naught is not compensated at all. You have the net current flowing through that. Forward bias, metal made positive, okay, metal made positive with respect to semiconductor. What happens now? Now, let me remove this point. Let us redraw that. I have drawn that already there. I just want to illustrate to you with that. You have here this barrier. Whatever you do, that side is not changing. So, thermal equilibrium, you had the situation where the Fermi level was here and you had the energy band diagram like this. Okay. That is thermal equilibrium. I am putting dotted line because when you forward bias FB, whatever barrier was there having a potential plus minus. If I apply plus minus there, like what you have done in the forward bias, you are reducing the potential across the device. So, whatever this Fermi level was equalized, that whole thing will now move up just exactly opposite to the reverse bias. So, this will be now like that and this will go like this. Okay, let me just draw that bit like that, go up. So, EC will go up from thermal equilibrium, EB also will go up and I can draw the Fermi level bit up there. That is a new diagram. What happens to the energy distribution? Originally it was like that. Please understand, dotted line was originally there, I do not want you to see it now. So, when I apply forward bias V, the whole thing will get shifted by an amount equal to V. So, the barrier will reduce by an amount V, forward bias. So, what will happen to this distribution? What was like that? This distribution, that will become like this now. Same thing, but it has gone up. That means, originally these were balancing each other, thermal equilibrium. Now, since the potential energy has gone up here, more number of electrons have the energy to cross the barrier from right to left. More number of electrons can cross. Okay. In fact, the electron concentration goes up exponentially as the voltage by Vt, V by Vt. That we will see a little later, but it is known that the carrier distributions vary from Boltzmann's law as proportional to e to the power V by Vt. So, if I increase the voltage here, the carrier concentration will go up as e to the power V by Vt, the ones which have energy above this. So, that means actually you will have the current which is flowing from right hand side to left hand side due to the transfer of electrons from the semiconductor to the metal. I put it as ISM. Okay, the symbols ISM means the actual current flow direction due to electron transfer from semiconductor to the metal. In order to avoid confusion, I put the arrow as actually the actual direction of current and I put it in the metal. The ISM I put in the metal region because the electrons which have got transferred onto the metal, which give rise to current in the metal, ISM. That current will flow through semiconductor also. And IMS, what is IMS? Current due to electrons which can cross the barrier from metal to semiconductor. That does not change. That does not change because that remains the same thing. So, you have I naught due to transfer from here to here and I naught into e to the power V by Vt due to transfer electrons from there to there. It is I naught into e to the power V by Vt because the carrier concentration has gone up by a factor e to the power V by Vt. Quantitative analysis we will do later. So, that is the thing. So, this is I naught and this quantity is I naught into V by Vt. So, net current flow is from the metal to the semiconductor, which is actually equal to here. Net current is due to ISM in that direction minus I naught in the other direction, IMS in the other direction. So, that is what is put here. So, we have got this equation governing the metal semiconductor contact. Okay. So, to see it once more, thermal equilibrium I naughts are same, reverse bias the electron injection from semiconductor to the metal goes down, barrier is increased. So, the current is only due to the transfer of electrons from the metal to semiconductor I naught, and the direction is semiconductor to the metal, okay? Because this side becomes positive, so the current flows in that direction. When you forward bias, in the case of N type semiconductor, metal is positive, semiconductor is negative, just like p-n junction. P type region you make positive, okay? Then I naught from here is not changing, but the other one is increasing. As a result, you have got the current like that, exactly like the diode. But the I naught that we are talking of in the case of metal semiconductor contact will be different in magnitude compared to the I naught of the p-n junction. That makes all the difference. Okay. So, you can see that reverse bias, it blocks the current because nothing is there, controlled by I naught. Forward bias, it allows the current to flow because lot of electrons are available to cross. Okay. Now, let us see. I just rewritten whatever I have been telling, so that you can have it here. IMS is current due to the electron flow from metal to semiconductor, which is I naught fixed for all the bias. ISM is current due to the electron flow from semiconductor to the metal, which is I naught into e to the power v by Vt. When you forward bias, so we are talking of forward bias, that is much large compared to I naught. Okay. So, net current is I naught into e to the power v by Vt minus 1. Okay. And the direction is from metal to semiconductor. When you make actually V in a reverse bias, that V is made negative, and then this term goes off. That term goes off, and you will get I naught. You put minus because you are putting the direction of current like this. When you write this equation, you write V as metal positive and the current direction as current entering into metal as positive. So, when you reverse bias that becomes minus I naught, telling you that current direction is reversed. This is the key thing what we have started. So, if you take a look at the equation of that metal semiconductor contact, I have drawn two characteristics, metal and N type semiconductor, and I have marked it here, the diode and the IV polarity, I is in that direction. So, this is the I naught e to the power v by Vt minus 1, and this is I naught. If I naught is large, how will the characteristics be? That is this one. I naught is large means the whole thing comes down here. What happens to the forward characteristics? I naught is very large. So, with small values of V, I get the same current. So, the entire thing moves like that, the characteristic. Now, it tells you the entire information that you are looking for. If I want to make a rectifying contact, I must have a p-n junction or a metal semiconductor contact whose I naught is very small. It will block the current in the reverse direction. If I want to make a ohmic contact, I must have a metal semiconductor contact which will have I naught large. When will I naught be large? That must be small. If I have a device or metal semiconductor contact with the low barrier height, I naught will be large, that will be ohmic. Okay? And what is that? What is that phi bn? In fact, this all we have just said over in the discussion now, that is I naught is that, and V is negative, it is minus I naught, all that. So, you need for ohmic contact, I naught should be very high. That is what we saw. Now, let me just go back to this curve and discuss before I wind up everything. So, ultimately what we are talking of in the case of N type substrate, we will talk of P type substrate in the next lecture, because we can't cover that. So, here what we want to make is phi bn small for ohmic contact, so that is large. Okay. And phi bn actually is governed by ideally that is the situation. So, I must choose a metal appropriately so that phi m minus chi is smaller. Okay. So, generally people say the phi m of the semiconductor, phi m must be large compared to phi of s. What matters is the difference here between phi m and chi. Smaller it is, closer it is to the ohmic contact. Larger it is, closer it is to the rectifying contact. So, we look forward to seeing what type of impact these metals really have in making ohmic contact and rectifying contact. We also will see in the case of p-type material what will happen. In the case of p-type material, you talk of phi bp rather than phi bn. So, if phi bn if I increase, you get rectifying in the n-type material. If I increase phi bn, what happens to phi bp? It decreases. So, in a p-type substrate, exactly opposite to what we see. You must have, if phi m is large in the case of p-type material, that will become smaller. So, this becomes larger. So, you will have ohmic contact there. That is all what we want to see. I think more about these thing we will see in our next discussion with energy band diagram for p-type material, and today I will stop on this discussion.